Right. Electrical potential energy. Um, that we are working with the fact that a change in potential energy is the negative of work. That comes from the work kinetic energy theorem. Um, and what we're going to do is look at the work to get to a location in order to know the potential energy at that location. Um, but we need to be very careful that the force acting through a distance, this needs to be the force from the electric field that you might be like Sisyphus pushing the charge against the field, but we do not want to know the force of you as you push the charge into location. We want to know the force that the field is exerting as you go to the new location. I hope that will be clearer when I get some images for you. That that well, here you go. We've got an image right here. Here's a positive charge, and I would like to know the potential at this, the electrical potential energy at this location, a distance r away from the positive charge. So again, the change in potential is equal to the negative of the work done, but this is going to be the force not of me pushing on this positive charge to get it to where I want it to go, but instead the force that the field is exerting, which is outward. We are going to adapt the convention that the potential energy at infinity will be zero, and so I'm starting at infinity and moving this positive charge in here, but the whole way in the force is going to be outwards, and the dr, remember, by definition, is always outwards. Even though my path is inward, that the dr that I'm working with here is outward, and so you have Coulomb's law, dr, and when you do the dot product of those two, it just becomes a positive quantity. But when you evaluate this integral, then this r to the negative 2 is going to become r to the negative 1 with another negative that comes out in front. And so the result that you get is going to be a positive value for the potential energy at some distance r from a positive charge. Notice again, when I talk about the potential energy at that location r, the assumption is I've gotten to r, that's my final location, and infinity was my initial location. So this change in u could be replaced by u if we have that understanding, because this is presumed to be zero. And there is the value for the electrical potential energy at r, with all of those assumptions. Most importantly, that at infinity, the potential energy is taken to be zero. Notice it looks rather like Coulomb's law with an r instead of an r squared. And that ought to seem right, that you were taking force times distance, and so force, which had an r squared, when you multiply it by distance, it ought to go down to just being an r there. So it should be easy to remember. To reiterate, the change in potential energy as you approach a positive will be a positive change. That you go from zero up to some positive quantity, and so the potential energy at some distance from a positive charge will be a positive amount of potential energy. Contrarily, if you are working with a negative charge and you want to know the potential energy some distance r away from it, again it will be a positive which you bring there, but this time as you travel in from infinity, you are going to have the dr in the opposite direction to the force that the field is exerting on your positive charge. And so when you do the dot product here, the force and the dr being in opposite directions yields you a negative, and that negative together with this negative yields this result with no negatives in it. And so the change in potential energy as you go from infinity to this location r, otherwise sloppily known as the potential energy at r, is going to be a negative quantity. When you evaluate this integral, we get a negative. So we have that as you approach a negative, the change in potential energy will be negative, and thus the potential energy at this location r is negative, with the assumption that the potential energy at infinity is 0. And so the graph of potential energy would look like this. What sort of charge would be here if you have a big positive spike? And the answer that people give is that it is a positive charge there at the origin. When you come in from infinity, the potential energy gets more and more positive, theoretically going to a very large value, perhaps infinity, as you get 0 distance away from the charged object. Okay, now I want to, and of course if this was a negative charge here at the origin, then we would flip this over and it would become a potential well that you would have here, that it would be go to negative infinity as you approached 0 distance. Next we introduce, instead of potential energy, that which is referred to as potential. And we need to be very careful to distinguish between the two. Potential energy, potential, otherwise known as voltage. And you may or may not recall from last year that this was defined as the change in potential energy per charge moved. Or this is equivalent to the negative work per charge moved. This is a definition that you need to make yours if it is not already yours. Okay, so we call this voltage, we call it potential difference, we call it electric potential, or we just call it potential. All of these names for this quantity. But please note, we never called it potential energy, just potential. This one would be potential energy. Units of electrical potential would be volts, which are equivalent to a joule per coulomb. And to reiterate what we were doing on the other side, but please note, in calculating this, and I worked this out just because I wanted it to work, so that it is again the work done by the field, not the work done by you as you push the charge in there, but it needs to be the force and the actual path. We do not want to put a dr there. Or the signs do not work out. As you approach a positive charge and the potential energy is going up and up, then if we were to use this with a dr, we would think that the work done, the negative of the work done by the field, we ought to get a negative, but we don't want that. I want the potential to also go up, to be positive as you approach a positive charge. And so, come on, you. That the force would be, if this was a positive charge here, would be away. And I want to, I don't know why I'm having so much trouble. I want to use dx and not dr, so that as you approach, the dot product of these two would be a negative, and that, coupled with the fact that we're talking about negative of the work, would yield me a positive. I want the potential to be positive as I approach a positive object. So I know that's the result I want, and I try to find some way to get there, like this kind of awkwardness here. So here, this was actually the picture in the book, and I pasted a U of R over top of it. This would be a potential spike that occurs if this is a positive charge here, and if it was a negative charge, you would have a potential well at that point. It goes down at that point. That, to reiterate, the change in potential, the potential difference, would be the difference between the final potential and some initial potential. But where do you think we're going to choose our initial potential to be? And that's going to be at infinity, and we will say that the potential there is 0. And so if we go from that 0 place, which was infinity, to this final place, and we take the negative of the work done, note here again the dx, the actual path that you're following, not this dr's. You have this is what we were working with on the previous page, and then I take F over Q, and that is equivalent to the field strength. So it is also true that the voltage is equal to the negative of the integral of field dot the path that you have followed. And we want to do much with this. Remember this formula. Remember the dot product. And we will go. But before we go on, just like to take a little sense of where we have gotten to. We have these 4 ideas now: electrical force, electrical field strength, electrical potential energy, and electrical potential. And these formulas only work for point charges, but that general sense that here you've got 2 Q's and 2 R's, and here you have just 1 Q, but still 2 R's. Here you have 2 Q's and 1 R, and here you have 1 Q and 1 R. So all the permutations of Q's and R's captured in these 4 ideas. And I will keep coming back to this to try to make it be a part of your consciousness. So we have this idea that when you are moving through a field, the change in potential is going to be the negative of the field dot ds. Well, that dot product is very cool. That to go from here to here, the change in potential there, or if you were to call this point 0, the potential that you have here relative to it, here the trip that you take is parallel to the field, and so you would get a positive out of that dot product, but then the potential is going to have this negative here, and so you are moving towards lower potential. To travel with the field is to travel to lower potential. Well, think about that. What do you know about the direction of an electric field? And you respond, it indicates the direction a positive charge would go if it were placed in that field. So what is the sign here? This would have to be towards the lower potential, and this would be the higher potential. That the positive charge would go away from high potential and towards low potential. And that's the result we just got from that analysis, that to travel this way is to travel to lower potential. It's going to be a negative change. Whereas to go the opposite way would be a positive change, and if you went the opposite way, then the dot product would yield you a negative, which together with this negative would make the quantity positive. Notice also that you can get between these 2 points, and when we talk about the potential difference, we just mean the difference between those 2 locations. But suppose you chose a trip like this. Well, here, during that trip, your path is everywhere perpendicular to E. And so that's going to yield you a 0. There is no change in potential between those 2. We call that we traveled along an equipotential. And then I do this trip, which is a much longer path, but the dot product means I'm only taking the component of that path which is parallel. That dot product means I'm only taking the component of the path that's parallel to E. Oh, well, that's identical to this. So moving between those 2 places, it doesn't matter what path you take, that you get the same result for the difference in potential between point A and point B. And you recall that when we say that something is path independent, that we say that the forces then are, and all the people say, conservative. So here again, we have this idea being developed that this is the definition of potential, and it's equal to this integral, but I can simplify the integral to look like this. And so if you're moving from this initial to this final position, then it's going to be path independent, and you ought to take the simplest path. And the simplest path, oh come on, would be one which has I'm going to move perpendicular to the field, so there is no change in potential there because the dot product yields you zeros when these 2 are perpendicular, and then I will move parallel to the field to get there. This would be the simplest path to evaluate, and that's the way you ought to do it whenever you are dealing with conservative forces, which you are with electric fields. Then the book has this exercise for you where they have shown you several equipotential surfaces. This one has everywhere voltage V1. This one has everywhere voltage V2, and so on. And then they ask you, what is the potential difference for path I? And the people respond 0. We're moving in an equipotential, so the difference in potential between there and there is the same. But for path 2, it leaves the equipotential and dips way down, and then comes up above, and then comes down, and ends here. What is the difference in potential between those 2 points for path 2? And again, the approach would be, let's take the simplest path we can, and so let's just travel within the equipotential surface, and we can see that the difference in potential is 0. If you travel path 3, the difference in potential would be V2 minus V1. And you get exactly the same result if you take this more convoluted path of path 4, that it's still going to be V2 minus V1. Here you have applications of that idea that electrical potential, V, is equal to the negative of the integral of the dot product of the field strength and the path that you have taken, and the fact that an equipotential then will always be perpendicular to the field line. So when you have a uniform field and the page I was photocopying got bent here, so they look like the field lines are bent, but they're supposed to be parallel, uniform field. Then you get field lines, equipotential surfaces, which are going to be all the same spacing apart and parallel to one another. Here you have a point positive charge, and you get these radial field lines. Notice how the equipotentials change their distance, because after all, the field gets weaker as it gets less dense, so you have to travel further through that weaker field to have the same change in potential. And it is convention that all equipotential surfaces are put the same difference in potential apart, so they get further and further. Here you have this, again, notice that the equipotentials, these dashed things, are always crossing the field lines perpendicular. And notice that we can see, because of the spacing of the equipotentials, that the field is strongest here, that you change voltage with smallest changes in distances here, and the field is weaker out here. You have to go further to get the same change in potential because of the weaker field. We could have also seen that by looking at the density of the field lines, but suppose we didn't have the density of the field lines and we only had the equipotential surfaces, we could look at their spacing to see the strength. How quickly does the voltage change? And here, it's kind of, there are blue equipotentials here that you can't see, that these are negative charges, and so these are potential wells. It's going down, and this is a positive charge, and so that's a spike in the potential. It's going up at that spot, but you just see that this is an application that allowed you to put charges of any magnitude you like, and then it would draw the field lines, but it also draws the equipotentials, emphasizing that perpendicularity between the two. Finally, we conclude with this essay from edition 6 of your book about these people in Sequoia National Park who said, "Whoa, this is way cool. Her hair is standing up." And so they decided to take a picture of it. And 5 minutes later, lightning struck and killing one person and injuring 7. That we humans think that nature is benign and does not intend to hurt us, but it does intend to hurt us. And we ought to listen. If you were a cow and you felt that electric field around you, you would get out of there. If you're a human, you smile for a picture. If we were to draw the equipotentials, these hairs are going to be along the field, and so if we go across those hairs perpendicular to them, we can map out the equipotentials, and I think the hairs ought to spread out, that we ought to find that the equipotentials get closer together here at the top of her head, so that is where the lightning is going to hit her, not here on her ear. And that concludes the lecture.